Now, coming to the introduction of low frequency control. So basically, in power generation, we'll be generating active and reactive power in thermal generating station, right? So in order to meet the active power demand, that means suppose if the demand is increased, so I have to increase the generation also. So to satisfy the demand value, obviously I have to regulate the generation also. Otherwise, the difference will be created in between the demand as well as generation. So due to this difference, the frequency might be vary, which leads so many problems which already discussed, right? So that is the reason we have to maintain the frequency as constant. To maintain the frequency as constant, we have to maintain a clear tolerance in between the demand as well as generation, right? So the excitation of generators should also be regulated to meet the reactive power demand also. So basically, the active power demand changes the voltage and reactive power demand changes the voltage. Sorry, active power demand changes the frequency and reactive power demand changes the voltage. So to control these two things, active power and reactive power, I need to control the frequency, I need to control the voltage. So that means to control the active power, I need to control the frequency. To control the reactive power, I need to control the change in voltage. So if we control these two things, I could able to control the total power system. So if I want to control these two things, if I'm going manual control mechanism, it is somewhat difficult, not somewhat, it is most probably it is difficult to maintain these two, that is active power and reactive power in appropriate values or required values. So that is the reason in any large interconnected systems, automatic generation control, automatic voltage regulators are used. So in this chapter, in this first unit, we are going to discuss about the automatic generation control mechanisms. In the second unit, we may go with the automatic voltage regulators. So these equipments are installed in each generating station to regulate these values for an interconnected, large interconnected system. So here already same point which already I discussed, change in active power depends mainly on the load or torque angle. So previously I told that load, now torque angle also depends. That means active power is mainly depends on load as well as torque angle. If these two values varies according to the variation of these active power as well as active load as well as load angle or torque angle, the active power will vary, and independent of this active power is independent of the voltage at the bus. So whereas if we are going with the reactive power, it mainly depends on the change in voltage at the bus, and it is not depending on the load angle or load value. So the speed of the generator can be regulated by using governor control. See here, if I want to increase the generation according to the incremental of the demand or decrease the generation according to decremental of the demand, I have to change the steam input which is coming to the turbine. So to control the steam input towards the turbine, it is possible through the speed governor control mechanism. So here in this chapter, one of the most important derivation as well as the concept is nothing but speed governor control mechanism. So which controls the inlet, increasing or decreasing the steam or water jet hitting the blades of the turbine. Suppose if we are using steam turbine, it controls the steam input. If we are using that means a hydel generating station, it controls the water input to the turbine blades. So in the similar way, the terminal voltage can also be regulated by using excitation controllers. which reduce or increase the excitation to the alternator. Because it is a synchronous generating station, synchronous generators does not start automatically. So it has to be provided with respect to starting methods. One of the starting methods is DC excitation. So this DC excitation control can be done with respect to automatic excitation controllers. Load frequency and excitation voltage controllers are non-interactive for small changes. So these two will not be interact for small changes. These two will be interacted for a large changes. So these less interaction can be modeled and analyzed independently. Separately, we are going to analyze these two things. That means active power control can be analyzed separately, and reactive power control can be analyzed separately. So this is the main block diagram of active and reactive power control. So here you observe here, this is the turbine. Turbine is connected with respect to a valve. This valve is controlled. That means valve position, either to open half or to open total valve or close the total valve. This valve control will be here, right? So according to the valve control, the steam input here, if I am considering this as a thermal generating station, the input is steam. If I am considering this as a hydel generating station, the input is water flow, right? So here I am considering thermal generating station. So steam is coming towards the turbine through the valve control, right? So now you assume that valve is controlled at X position. Now some amount of the steam is coming and hitting the turbine plates. According to this particular steam value, turbine is rotating. You assume that it is rotating with respect to the synchronous speed. So as this turbine is mechanically coupled with respect to the alternator, so alternator is nothing but synchronous generator. Synchronous generator is not a self-starting machine. So the starter is excited with respect to controllable excitation, right? So whenever it is excited and the input is provided to this particular generator, so it will generate active power as well as reactive power. Why I am considering change in active power and change in reactive power? Because here on this particular lines, a load is connected. So with respect to load variation, this active power and reactive power generation could also be changes. So that is the reason I mentioned here as change in active power and change in reactive power. So now according to the load, I have to sense frequency value with respect to frequency sensor, right? So load frequency, this frequency value is given to the load frequency controller. We'll discuss what is load frequency controller later. So this frequency value is given to that particular load frequency controller. Previously it was 50 Hertz. With respect to the change in demand, the frequency is reduced to 49.8. So 49.8 value is given to this load frequency controller. So basically reference frequency is 50 Hertz and this particular measured frequency is 49.8 Hertz. So difference is 0.2 Hertz. That error value will be given to the valve controller. That error value is in terms of Hertz, and it in load frequency controller it converts it into a distance, because the valve controller will be controlling the valve position. Position is measured in terms of meters or centimeters. So that is the reason it converted as a distance. So that information will be given to the valve, so that automatically valve position will be controlled to either increase or to decrease the steam input value, right? So next, here according to the DC excitation, here again voltage is sensed. You assume that 415 volts, the output should be 415 volts. Voltage sensor senses the voltage, and QV controller, that means reactive power controller, change in voltage control or change in reactive power controller. And according to 415 volts, it gives the excitation. That means it required to get the 415 volts. So it is giving some amount of the excitation. That means you take X voltage, right? So now due to the incremental of demand or a voltage drops in a particular line, the voltage value is measured as 405. That means 10 volts of difference is present in this particular line. So the voltage sensor senses the 405 volts and gives the particular 405 volts to the reactive power controller. Here it compares the reference voltage and measured voltage. There is a 10 volts of difference is present in this particular. So that value, that 10 volts difference is given to the controllable excitation to increase the 10 volts to get the output voltage as 415 volts to maintain the V by F ratio as constant, right? So this is the explanation of complete block diagram of a power system control, right?